Here is an example of a good DTA solution. In this example, I'm comparing two different algorithms. One is a commonly known one called the MSA method of successive average, and the other is the GFV algorithm, which is also used in Dynasty. We first look at a baseline case, which is depicted by this graph in the upper left corner. The dotted line represents the MSA method, while the solid black line shows the GFV. The y-axis represents the relative gap, and as more and more iterations are completed, the gap starts stabilizing and reaches a minimum value. As you can see, the GFV is able to converge much better than the MSA algorithm, and even after 100 iterations, the MSA model's gap is still changing. This situation is called a cold start, where we begin with only our OD tables and run the simulation until it reaches convergence. The bottom left table, on the other hand, shows what is called the warm start. This is when the very first iteration is based on vehicle and route information drawn from a previous dynamic UE case. The warm start loads that information at the beginning of the simulation and continues from there. In this case, we can see that although there are some perturbations for the GFV model, the gap goes nowhere as high as in the cold start and converges much faster. In this other graph in the center, we simulate a work zone by adding a perturbation in the model by reducing the capacity of the particular link marked on the map on the right. In the first few iterations, the gap function increases as vehicles need to be diverted. Vehicles that used to go through the link experience longer travel times. However, as the model goes through more and more iterations, the gap function is reduced and convergence is reached. Through these examples, we can consistently see that the MSA algorithm has a higher gap function than the GFV one, and can determine that the GFV performs better than the MSA. We would also like to look at the stability for these algorithms. Given the same work zone scenario, we look at different OD pairs to see how stable their solutions are. OD pairs that aren't affected by the work zone link should not have their traffic volume change dramatically. Zone pair 1 to 2 is a freeway with two separate endpoints. The work zone is next to it, facing the east-westbound direction. The interaction between the work zone and traffic going through the freeway should be fairly minimal, so reassignment of routes shouldn't drastically influence the traffic dynamics for vehicles traveling between zones 1 and 2. The y-axis for these graphs shows the so-called coefficient of variation for all of the vehicles taking different routes between the origin and destination. In the graph on the right, this thick, dark line on the bottom is called the GFV baseline. The GFV work zone is the other solid line beside it. After reassignment for different departure times, vehicles still have pretty low coefficients of variation, meaning that the travel times are similar. We take the different times for all the vehicles and compute their standard deviation. The coefficient is found by taking that deviation and dividing it by the mean. The dotted line here is the MSA baseline, and as you can see, it's all over the place with radical variations. The used routes and travel times are often extremely different, and the MSA work zone case also has fairly high coefficients of variation. A similar pattern can be found when using zones 9 to 13 instead as the OD pair. This pair should be affected significantly by the work zone, and once again we can see overall that the MSA model has much larger coefficients of variation compared to the GFV one. This is another way of examining the quality of the algorithms from the standpoint of their stability.